1, this is going to be the recording going over day 7, the quotient rule, and then introducing day 8, the derivatives of the other trigonometric functions. The next time we see each other in class will actually be on Thursday, and we'll be reviewing for the unit test during that day. Really sorry about missing all of this class. Really wasn't intentional. Friday I took off because I had to write college recommendations, and then of course we didn't meet Monday. Today, Tuesday, I had to cancel class because I had to take my dog into Angel for emergency, and then tomorrow I'm at work, but I have a professional development in the middle of the day, and so D block is canceled tomorrow as well. So really sorry for having 3 classes in a row canceled like that. That's really not my intention, not something that I would normally do, and yeah, really sorry about that, but the stars kind of lined up against D block in this way. But rest assured that between the videos and when we do meet in class on Thursday, we'll definitely have plenty of time to prepare for the test. So with that said, let's get started. I want to begin by going over some questions from day 7, from the quotient rule day. First of all is number 6, which is about the difference between L'Hopital's rule and the quotient rule. They kind of feel similar because in both cases you have a fraction and you're doing some kind of differentiation. So what's going on? First of all, when it comes to L'Hopital's rule is something that is used to find the value of a limit. All right, it is used to find the value of a limit. So you should only be using L'Hopital's rule if you see a limit, like you do here in part A of number 6. The quotient rule is used to actually find the derivative of a function. So let's see what the difference between those two things is. The limit here, we need to use L'Hopital's rule. And first of all, we should make sure that you can use L'Hopital's rule. L'Hopital's rule says that if you get 0 over 0 in the fraction when you plug in, and you do here, then you can take the derivative of the top and bottom and try again. So that is what I'm going to do. I'm going to, let me open up a new document really quickly. My equation editor is being a little bit crazy here. So I'm going to take the derivative of the top and the bottom. The derivative of the top is cosine x minus 1. The derivative of the bottom is 2x. If you plug 0 into this, I think you actually still get 0 over 0, which just means that you have to use L'Hopital's rule again. In other words, you have to take the derivative of the top and the bottom a second time. The derivative of the top this time is just negative sine of x, and the derivative of the bottom is just 2. And if you plug 0 into that, then you get 0 over 2, which is just 0, and so that's the value of the limit. So that's L'Hopital's rule. L'Hopital's rule is about evaluating limits, and it says that if you get 0 over 0 when you plug the number in, then you may take the derivative of the top and bottom and try again. The quotient rule is used in order to find the derivative of a function. So if I want to find the derivative of this function, let me just copy it here. If I want to find the derivative of this function, then I need to use the quotient rule because this fraction is a quotient. The quotient rule is not simply the derivative of the top over the derivative of the bottom. You are not simply taking the derivative of the top and bottom of the fraction. Rather, the quotient rule, let's recall exactly what it says. It says f over g prime is equal to f prime g minus fg prime all over g squared. That's the quotient rule. Very different from L'Hopital. So applying the quotient rule to this function, I need to take the derivative of the top, that's f prime. Derivative of the top would be cosine x minus 1 times the bottom left alone, so that's just x squared, minus the top left alone, so that's just f, that's sine of x minus x, times the bottom left alone, that would be 2x. All over the bottom squared. The bottom is x squared, so if you square x squared, you'll get x to the 4th. So that is the derivative that you get applying the quotient rule. You can simplify this, but I'm not too worried about the simplification. The point that I'm trying to make with this problem is how different these two processes are. In this first problem, you're taking a limit, And L'Hopital's rule says you can take the derivative of the top and the bottom. Here, you're taking a derivative, and you need to use the quotient rule. And the quotient rule is not simply taking the derivative of the top and the bottom. Rather, it's this complicated formula. So make sure you know the difference between those two things. The second one I wanted to do 7a, which was about finding the derivative of cotangent. So let's just set that up. So we're going to find the derivative of cotangent x. And in the problem, I tell you that the way to do it is to rewrite cotangent x as cosine x over sine of x. And so if we want to find the derivative of cotangent, that just means finding the derivative of cosine over sine, and we can use the quotient rule for that, because of course it's a quotient. So quotient rule says take the derivative of the top, the derivative of cosine, that is negative sine. So that's the derivative of the top times the bottom left alone, so that's sine of x left alone. And then minus the top left alone, so that's just cosine x, times the derivative of the bottom is cosine x as well, all over the bottom squared. So you could write sine squared x. So that's what we get when we apply the quotient rule. It can be cleaned up quite a bit. That's going to be equal to, well, these two terms here, negative sine times sine, that's just negative sine squared x. These two terms here, minus cosine times cosine, that's just minus cosine squared x all over sine squared x. Now, the thing that you might notice about the numerator in this expression is that both terms are negative, and so you can actually factor out a minus sign, which is like factoring out a -1 if you prefer. If you pull the minus sign out of those two terms, you're left with sine squared x plus cosine squared x all over sine squared x. And then if you remember anything about trig identities last year, you should remember that sine squared plus cosine squared is 1. So in fact, this whole expression simply turns into -1 over sine squared x. And you might remember that sine is the reciprocal of cosecant. So 1 over sine would be cosecant. This is -1 over sine squared, so this is actually equal to negative cosecant squared. So the derivative of cotangent is negative cosecant squared, as claimed. You shouldn't worry too much about using fancy trig identities. You know, they're showing up in these problems, but it's not like we're going to have you doing a bunch of trig identities on the test or anything. And then the last one that I want to do from the quotient rule is this one right here, number 8. This is a tough one. There's a lot of chain rule stuff that can mess you up, so let's do it. So first, let me copy. We want to know the derivative of the function is right here, so let me just copy that. It is y equals x minus 3 to the 4th all over 2x minus 1 to the 3rd. So that's the function whose derivative I'm going to find. So first of all, we need the quotient rule. It's definitely a quotient of two functions and can't be rewritten or anything. So we're going to use the quotient rule. So quotient rule, let's recall one more time what it says. The derivative of f over g is equal to f prime g minus fg prime all over g squared. So there's the quotient rule. We're going to apply that. So what will our derivative y prime be? Well, first we need to take the derivative of the top, right? That's going to be your f prime, times the bottom left alone. The thing is, though, you might notice that the top and bottom functions are themselves fairly complicated, like their compositions. And so I think that it's actually safer, instead of trying to figure out the derivative of this function right now, I'm just going to put it in brackets and write a prime. So I have f prime g. I'm just going to write this expression in brackets, x minus 3 quantity to the 4th, and put a prime to indicate, hey, that's f prime. That's the derivative of my top function, times the bottom function left alone, so that's just 2x minus 1 to the 3rd. And I'll figure out what this derivative actually is in the next line. And then minus, okay, f, that's the top function left alone, so that's x minus 3 to the 4th, times the derivative of the bottom function. And again, I'm just going to write that bottom function in brackets and put a prime on it to remind myself to find the derivative of that function in the next line, all over g squared. So if I take the denominator and square it, well, that 2x minus 1 is already being raised to the 3rd. So if you raise it to the second power, those exponents will multiply. 2 times 3 is going to give you 6. So you have 2x minus 1 to the 6th power. And, the reason I'm sort of postponing the differentiation here and here is because having to think about the chain rule inside and outside and all that stuff while you're in the middle of an application of the quotient rule can be pretty confusing. It can be easy to get lost. And doing it this way makes me be able, it allows me to simply focus on the quotient rule and worry about chain rule stuff later. So that's why I recommend it for complicated functions like this. So now in the next line, we're actually going to have to compute these derivatives. So I need to figure out the derivative of this term here. That's a composition. The x minus 3 is stuffed inside of the blank to the 4th function. So the outside function is blank to the 4th. Derivative of the outside function is 4 blank to the 3rd. What goes inside the blank? It's just the original inside function, x minus 3, times the derivative of the inside function. But the derivative of the inside function here is actually just 1, right? The derivative of x minus 3 is just 1. So that 1's not really doing anything, but I wrote it anyway. Okay, times this guy just left alone, right? I don't need to compute any derivatives there, so I'll just copy it, minus, and then this guy, again, I'm just copying it, no need to take any derivatives, x minus 3 to the 4th. But then I do have to compute the derivative of this guy. That, again, is a composition. The outside function is blank to the 3rd, so the derivative of that will be 3 blank squared. What goes inside the blank is the original inside function, 2x minus 1. But then I'm not done because I also have to multiply by the derivative of the inside, which is 2. And if you are having trouble with this problem, there's a 90% chance that this little 2 right here is exactly the thing that you missed. So check your work if you are having trouble. All over 2x minus 1 to the 6th. And so that's the derivative. It just needs to be simplified. I noticed that there's probably a lot of common factor stuff that can be pulled out of the numerator. So that's what I'm going to do next. I'm going to pull the greatest common factor out of both terms in the numerator. Right, so this whole thing here, that's one term, and then this whole thing here, that's the other term. So what's the GCF? So as far as coefficients are concerned, there's a 4 here, there's a 3 here. 4 and 3 don't share any common factors, but there is a 2 here. So it seems like as far as the coefficients are concerned, all that I can pull out is actually a 2. So I'm going to pull a 2 out of the 4, and I'll just remove the 2 from here. What else do we have? We have x minus 3s. Both terms have a bunch of x minus 3s. The maximum number that I can remove from both terms is 3, right? Because this first term only has 3 copies of x minus 3 to give. And then finally, I have copies of 2x minus 1 in both terms, and I'm going to remove as many copies as I can. The maximum number that I can remove is 2, because this term only has 2 copies of that term to give. So I'm going to pull out 2 copies of the 2x minus 1. And then a set of brackets, and I'm going to write whatever's left over inside these brackets. So what is left over? Well, from this term, I pulled the 2 out of the 4. That leaves me with a 2. I removed all 3 copies of x minus 3 from this term, so there are no more copies of x minus 3 left. But I removed only 2 out of the 3 copies of the 2x minus 1. Therefore, I've still got a copy of 2x minus 1 left in that term. And then I have this minus sign, so I'm going to write minus, and now I ask what's left over in this second term after removing the greatest common factor. Well, I removed 3 copies of the x minus 3 from this term, so that means I've still got 1 copy of x minus 3 left. I've still got this multiple of 3 sitting there. That wasn't removed. I think that both of these copies of the 2x minus 1 were removed because I only had 2 to begin with, and I removed 2. And this coefficient of 2, if you remember, that was removed. That guy's sitting out over here. So I think that the x minus 3 times 3 is actually all that I have left over in that second term. And I'm just going to recopy that denominator, 2x minus 1 to the 6th. And now, basically, you'll notice that there's some, canceling of common factors that you can do here because we've got some copies of 2x minus 1 on top and also on the bottom. So if we cancel those, we're left with 2 times x minus 3 to the 3rd These guys are canceled, so we're not going to write those. Then we have the expression in brackets. Of course, while I'm at it, this expression in brackets, you might notice it can be simplified if you distribute the 2 to this term here, and then you distribute the minus sign and the 3 to these 2 terms here. You're going to wind up with a bunch of stuff that can be combined. Let's go ahead and do that. If I distribute the 2 to these 2 terms here, I'm going to get 4x minus 2. And then as far as this guy is concerned here, you got to be really careful because both the 3 and the minus sign are hitting both of these terms here. So in fact, it's going to be minus 3x, but then plus 9, right? 3 times 3 gives you 9. Well, this would be a negative 9, but then this minus sign makes it a positive. And then we canceled 2 copies of the 2x minus 1 from the top and bottom. So on the bottom, we just have 4 copies left over. And then if I simplify this expression in brackets by combining like terms, I will finally be done with this wretched problem. So yeah, so what do we got? 2 times x minus 3 cubed. In brackets, I think you've got 4x minus 3x is just 1x. And then minus 2 plus 9 is plus 7. All over 2x minus 1 to the 4th. Wow. Okay, that is a pretty nasty problem. But I would say the main thing to watch out for, guys, be really careful in your initial application of the quotient rule. I strongly recommend you do this sort of trick where you postpone the differentiation, because if you don't and you try to do it all at once, there's just a very good chance that you're going to forget to use the chain rule, which is what gives you this times 2 at the end here. Okay, so great. That is the quotient rule stuff. Let's move on to day 8. So this is where you should be taking notes. Day 8, we are really just going to summarize the trig derivatives that we learned last time and do some practice. So I'm going to go ahead and open up the worksheet now. So first of all, what you should be copying into your notebook and the notes that I want you to take is basically this right here. So between yesterday's worksheet and stuff that we learned a long time ago, we actually now know the derivatives of all 6 trig functions, right? The derivative of sine is cosine, you've known that for a long time. The derivative of cosine is negative sine, you've known that for a long time. But we also saw that the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant times tangent, and the derivative of cosecant is negative cosecant times cotangent. You need to know all 6 of these formulas, okay? You need to know them for the test. The good news, though, is that you will actually get quite a lot of credit on the test simply for regurgitating or remembering these pure formulas. We'll give you quite a lot of credit just for memorizing them. And in a way, that's really good because it means, hey, I can get a lot of points just for memorizing a formula, right? Not really any thinking involved. So you need to know these 6 formulas. Obviously, you already know 2 of them, I hope. As far as the others are concerned, I want to point out that these formulas here are arranged in this table in the order that they're in for a particular reason. I've arranged them in a very specific way that makes the memorization a little bit easier. I want you to focus on, for example, this guy here compared with the entry below it. Do you notice that they're basically the same except for 2 things? Every function that you see in the top row is replaced with its co-function in the bottom row. Like secant is replaced by cosecant. Secant is replaced by cosecant. Tangent is replaced by cotangent. That's one difference, and the only other difference is that there's a minus sign. And that is actually true all across the row. If you look here, this item, this row entry versus this entry, again, they're the same, except each function is replaced by its co-function, and there's a minus sign. So tangent, cotangent, secant, cosecant, and the minus sign. And that's true all the way through. That observation helps you to remember. I find that basically I really just kind of memorize these 2 right here. and then I know how to find the other ones from this observation that you just switch all the functions with cofunctions and put a minus sign. So that's a good observation for helping you to memorize these guys. So let's go ahead and do some examples. I don't want to find the derivative at pi over 6. So let's find the derivative of this function right here. As you've sort of noticed on some of these worksheets, people are not super good about writing their parentheses on trig functions. So just to be clear, that function means tangent of 4x. It doesn't mean something weird like tangent of 4 times x. That's what this guy means. So we want to take the derivative of this thing. What you should notice is that this is a composition. You've got one function stuffed inside of another, so it's the 4x stuffed inside of the tangent blank. So we need to use the chain rule. So chain rule says you need to take the derivative of your outside function. The outside function is tangent blank. And what's the derivative of tangent blank? Well, if you look at your table, the derivative of tangent is secant squared. So the derivative of tangent blank must be secant squared blank. So that's the derivative of the outside function. What goes inside the blank? Well, just the original inside function 4x. But you're not done. The chain rule says you still have to multiply by the derivative of the inside function, which is 4, and so that's our derivative. Maybe you could put the 4 up front. Coefficients kind of belong up front, but whatever. That's basically it. So that's a pretty fast example. Let's now look at a more complicated one. So let's have a look at, I'm going to delete these because these are the notes that I'm just about to type in front of you. So let's have a look at this function. We'd like to find the derivative of 2 secant of 5x. So I hope you agree that, again, this is a composition. The outside function is really, so let me just write it. The outside function is really 2 secant blank. I hope that you can see that the outside function is 2 secant blank and the inside is 5x. So we need to, according to the chain rule, take the derivative of the outside function. What's the derivative of 2 secant blank? Well, you got to remember, what's the derivative of secant? If you scroll up and look at the formulas at the top of the page, the derivative of secant x is secant x tangent x. Okay, the derivative of secant x is secant x times tangent x. And so the derivative of secant blank must be, well, the derivative of 2 secant blank must be 2 secant blank tangent blank. It's awfully strange that you get 2 blanks when you do this. This is the first time that this has ever happened in our study of the chain rule, but it does happen with secant and cosecant as well. You get these 2 blanks when you do the chain rule. So that's the derivative of the outside function. What do we do with these blanks? Well, you stick the inside function into the blanks, both of them. So in fact, both blanks get a 5x, but then you're still not done because the chain rule says you also have to multiply by the derivative of the inside function, which is 5, and that's basically the derivative. We're done. Maybe the 2 in front here and the 5 in front here should be multiplied to 10, but otherwise that's basically it. So there's our derivative. And then finally, let's do one more example. Let's have a look at x cosecant of 3x right here. So let me delete the notes from here. So how do we do this? Well, first of all, you should notice in this function that you've definitely got composition, like you've got 3x inside of the cosecant function, but there's also a product structure happening. There's an x times this function. So you're going to need the product rule and the chain rule. And I would say you're going to need to use the product rule first because fundamentally this function is a product. It's one function times another. There is a composition structure happening, but it's only a piece of the function that is a composition, not the entire thing, whereas the entire thing really is a product. So product rule first. And what I'm going to do, sort of recognizing, as often happens with these, sort of recognizing that the functions involved are complicated, that I'm probably going to have to be doing some kind of weird chain rule stuff. I'm going to be very careful when I do the product rule, and I'm going to postpone the differentiation, right? So product rule says take the derivative of the first function. So, okay, that's just the derivative of x. Now I know that that's 1, but I think that I'll just leave it. And then times the second function just left alone. Plus, now I leave the first function left alone, that's just x, times the derivative of the second function. I'm just going to write the second function and put a prime. So that way, I don't have to think about the chain rule as I'm carrying out the product rule. I'm postponing all the actual chain rule stuff until the next line. So what will that give us? I think that we're going to get y prime equals, so the derivative, obviously the derivative of x is just 1, so 1 cosecant of 3x. You don't need to write the 1, but whatever. Plus x times the derivative of this guy right here. Now that term, the cosecant of 3x, that is a composition, and so we're going to need to use the chain rule. The outside function is cosecant blank. So what's the derivative of cosecant blank? Well, we should remind ourselves what's the derivative of cosecant. Derivative of cosecant is negative cosecant times cotangent. So the derivative of cosecant blank must be negative cosecant blank times cotangent blank. So let's go ahead and write that down. So we're going to get times negative cosecant blank cotangent blank. So that's the derivative of the outside function. What goes inside the blanks? Well, just the original inside function, 3x. It goes into both of the blanks. But then we're still not done because we still have to multiply by the derivative of the inside function, which is 3. And so that's basically the derivative. It can be cleaned up a little bit. We can say that this is y prime equals, well, so let's see. So the 1 isn't really doing anything here, so that's just cosecant 3x. And then the whole second term, this is all one term. It's all being multiplied. Because of the minus sign that's sitting right here, the whole term becomes negative, so I'll write a minus. It's good form to put the coefficient, the 3, out in front on the left. So I'll write minus 3, and then this x, so minus 3x, and then the trig functions, cosecant 3x times cotangent 3x. And that is our derivative. That's about it. You could pull out a common factor of cosecant 3x if you really wanted to, but that's it. And so that's all I have to say for this unit, or for this lesson. So you can go ahead and work through the exercises. I will, however, I think, just talk about 1C a little bit because in class, when I gave this lesson, a lot of people were having trouble on this one, and it is kind of a funny problem, I guess. So the way to see 1C, no pun intended, is to say, well, anytime you have a power of a trig function, you really, really need to rewrite the trig function. So I would say that this is y equals 5 times cosecant x all raised to the second power. That is how I would rewrite that function before taking the derivative. So now that it's written that way, you can see clearly that the outside function is 5 blank squared, and so taking the derivative of the outside function will give you 10 blank to the 1. What goes on the inside of this blank? Well, just the inside function, which is cosecant x. But then we're not done because we still need to multiply by the derivative of the inside function. And what is the derivative of cosecant x? Well, it's negative cosecant x cotangent x. And that's the derivative. It can be cleaned up a little bit because, of course, we've got 2 copies of cosecant being multiplied, and this negative should be put out front. So I would say it's negative 10, and then with the 2 copies of cosecant, that's cosecant squared x times cotangent x. And I would say that that is the derivative right there. A few other comments about things that people might ask about in this worksheet. This problem here, g, you're going to have to find the derivative of this function. This is going to require the product rule because you've got x times this other stuff here, but it's also going to require the chain rule because this guy right here is a composition. The outside function is f of blank, and the inside function is x squared. So so be careful about that one. This guy here, this is a limit problem. Guys, if you see a limit problem, there's a very high chance that it's a L'Hopital's rule problem, but just make sure that L'Hopital is actually applicable, which means if you plug in pi, do you get 0 over 0? And the answer is yes, you do, which means L'Hopital's rule is applicable, so you're going to take the derivative of the top and the bottom and then try again. The derivative of the top is just 1 because pi is a constant, right? The other thing is a lot of people asked about this problem right here. The final answer that we give in the answer sheet, they factor out a copy of x to the 1/3. So your answer is probably correct. They're just pulling out a factor of x to the 1/3, and that is what gives them their answer. So watch out for that. And the last thing that I'll say about this is, after learning about the product and quotient rules, people kind of make a mistake of applying, without thinking, the product and or quotient rule every single time they see a product and or quotient. But the thing is, sometimes it's actually a lot faster to rewrite the function and avoid using the product or the quotient rules. And that's kind of what these problems are getting at here. We point out that only one of them really requires the product rule. You can use the product rule on all of these. You absolutely can, but you're going to make a lot more work for yourself, okay? This one here can just be FOILed out. It FOILs out very nicely, and then you can take the derivative. This one here, x times root x, that's just x times x to the 1/2, which is x to the 3/2, right? That's very easy to find the derivative of that, right? That's just 3/2 x to the 1/2. Don't use the product rule on this guy. This guy here can be simplified as well because tangent is actually just sine over cosine. So if you make that replacement, the cosines will cancel and you'll just get sine. This guy, on the other hand, really does require the product rule. No way of getting around that. And then in problem 3, we have a very similar question. You know, just because you see a fraction bar doesn't mean that you need the quotient rule. You could use the quotient rule on every one of these problems, but most of them, there's something to be done and simplified before you do the quotient rule. Like, look at D here. Yeah, technically that's a quotient, but the thing is, sine 8x over 4 means the same thing as 1/4 sine 8x, right? So that's the same thing as just 1/4 times sine of 8x. That really shouldn't be thought of as a quotient, right? That's really, this requires the chain rule, but that's it, right? So just because you see a fraction bar doesn't mean automatically jump to the quotient rule. Likewise, this guy here, yeah, it's a quotient, but you can split the fraction, right? You can split the fraction. We did problems like this in Unit 2, right, before we knew the quotient rule. I think this guy really does require the quotient rule. I don't think there's any kind of trick that you can do with this one. Fractions like this can't be split, right? And then this guy here, I think that cosecant times secant is something nice. If you think about what it is, you'll see that cosecant times secant is actually a pretty nice thing. On the other hand, if you try to use the quotient rule on some of these problems, you're going to be here all day. So just be aware that sometimes it's better to simplify and to rewrite before you go using the quotient rule. Okay, all right, guys, so that is it for today. I will see you all soon.